Okay, this is for Astronomy 320. This is the updated PowerPoint slide. So if you already downloaded this, I just uploaded a new one. It's 7:36 on Thursday night. So I just uploaded the new one about, I don't know, 15 minutes ago. So you want to get this one. Okay, so this is the updated one. I've also updated this guy. Okay, doesn't say that this is tentative anymore. This is the material that'll be for quiz 3. I'll put out another video tomorrow or Saturday where I'll go through these questions. Okay, so let's go through the PowerPoint right now. Basically, I just got through behavior of light. So chapter 2, stuff we covered in chapter 2 plus this first part of chapter 5. We're skipping chapter 4. We got to get to the stars. This is stuff we need to know for stars. So light comes from stars. What is light? Okay, light is a wave. A wave is a disturbance in a medium. So for example, water is a medium. The medium is what the wave can move through. Air is a medium for sound waves. Sound waves move through the air, the atmosphere. And then just light waves actually move through an electromagnetic field. So in that case, an electromagnetic field is the medium for light. But just to try to keep things simpler, a wave is a disturbance in a medium. You throw a rock into a placid lake, you disturb the water, and the water moves out from the disturbance. So the water is the medium, and the disturbance that moves out, that is the wave. Okay, disturbance in air creates a sound wave. When you talk, you disturb the air molecules and produce a sound wave. That sound wave can then carries energy from your mouth to the ears and to the ears of others. Okay, I cannot run the simulation for Newcomb's thing anymore because Sac State, I'm borrowing a Sac State computer and it does not want to let me use Java period with all their antivirus stuff on there. So you may be able to run this. I can't run it here. What medium do we disturb to create a light wave? We are surrounded by an electromagnetic field. It is everywhere throughout space. A disturbance should be in the electromagnetic field produces a light wave. So now think of it. This is an electromagnetic field. It's something you cannot see. It's something you can't touch. But let's think about another kind of field that we may be a little bit more familiar with. Okay, a field is a region in space where you can define a data point everywhere. So, for example, you could go around the room you're sitting in now with a thermometer, and you could map out what the temperature is all throughout the room. You can see maybe closer to the floor, it's a little cooler. You go up towards the ceiling, maybe it's a little warmer. So you could map out data points for throughout the entire room. Okay, that'd be a field. Okay, so a gravitational field surrounds the Earth. If we place a mass somewhere near the Earth, it will experience a gravitational force. The force will be stronger closer to the Earth and weaker farther from the Earth. We can go around and measure the different forces the mass would experience at different locations around the Earth. Okay, so we put something close to the Earth, it feels a big force, gravitational force toward the Earth. We put it further from the Earth, we measure that gravitational force, we see what's smaller. We can write the numbers in there, say this is what it is up here, this is what it is up here, this is what it is over here. So we're mapping out a field. In this case, we'd be mapping out a gravitational force field. Now, in electromagnetic situations, we also have fields with forces. So electrons and protons, they are attractive. So here you got your proton here, you got your electron there, and the electron's closer to this proton, so it feels a large positive force towards this electron. This proton way over here, that feels a very small force. Now what if we move the electron? We moved the electron from here, now it's way over here. Now suddenly this guy feels a much smaller electromagnetic force. This guy went to a big electromagnetic force. We disturbed the electromagnetic field. We cause a disturbance by moving the electron. And then what we can do is keep moving it back and forth, back and forth, back and forth. That continues to send out electromagnetic waves that basically the disturbance in the electromagnetic field by just vibrating that electron back and forth. Okay, now we need to understand these following things. Wavelength, that is the distance between two identical consecutive points on a wave. So we can go from this peak to this peak. And by the way, this would be a complete cycle, wherever the wave starts to repeat itself. So here we got a peak, we go down through equilibrium. Equilibrium is where the medium would be if there was no disturbance. In other words, going back to the water picture way back up here, if there was no disturbance here, the medium, we'd have a placid lake, it'd be flat. That would be equilibrium. Then we throw the rock in there, the waterways bounce up and down past equilibrium, up and down through equilibrium. Okay, so equilibrium is where the medium would be if there was no disturbance. Okay, so now we've got, then also from here to here, from here to here would also be let me try something. Never mind, what I tried didn't work. Okay, so from there we go up away from equilibrium. Now we go down through equilibrium. So that's not repeating itself, but it's repeating itself here. Or we could say there it's going down through equilibrium, it's going up through equilibrium. That's not the same thing. Then we go down through equilibrium. So from there to there would also be a complete cycle. So the length of that cycle, that's the wavelength. The distance between two identical consecutive points on a wave. We should get the same number no matter where we measure it from. It's denoted by the Greek letter lambda, which looks like that. It's wavelength. Units are in distance: meters, feet, miles, yards, kilometers, whatever. Anything that's a measurement of distance or length. What's going on there? Okay, now another one we need to understand, not so much as wavelength, but the other one is amplitude. Amplitude, the distance from equilibrium, that's where the medium would be if there was no disturbance, to the crest or peak of a wave, the highest point. So this would be equilibrium here. The wave vibrates back and forth, up and down through equilibrium, and so we measure to the highest point above equilibrium. That is the amplitude. You could also, we could also measure downwards from there to there, but most people just go from equilibrium to the highest place. Wave speed, that's how fast the wave is moving. Okay, how fast is it moving across your screen? Wave speed V as units of meters per second or feet per second or miles per hour, etc. Anything that's distance over time, that would be wave speed. And then terms we need to understand: frequency. How often does a wave repeat itself? Okay, cycles per second. Frequency F has units of hertz, H-E-R-T-Z, named after Heinrich Hertz. Now, so in other words, how many cycles do we have? How many complete cycles do we get in a single second? That is what frequency is going to be. How frequent are these cycles? Okay, cycles per second. Period, on the other hand, is seconds per cycle. How long does it take for to have a complete cycle, for a wave to complete a cycle? Okay, how long does it take for us to get from one peak to another peak time-wise? How long does that take? It's seconds per cycle. Period T has units of seconds, minutes, and days, and so on. Okay, mathematical relationships we need to understand. Frequency is in cycles per second. Period is in seconds per cycle. Frequency equals 1 over period, and period equals 1 over frequency. Okay, remember they're inverses of each other, right? They're inverses of each other. Frequency is cycles per second, and period is seconds per cycle. Then they're inverses of each other. Okay, wave speed, well, you take a distance. Well, we've got a distance, that's the wavelength. The wavelength is how far the wave would have traveled when it completed a cycle. Time is how long it takes it to complete the cycle. So wave speed equals wavelength times divided by period. But we say, well, wait a second, frequency equals 1 over the period. So there's wavelength over period. I could write this as wavelength times 1 over the period. So wavelength times frequency, that's also equal to the wave speed. And we're going to do this one next time. Okay, so now there's some mathematical relationships you want to understand. And I think that's everything. Hopefully this won't take too long to upload. And I'll probably be sending out you'll already have gotten email when you see this. Okay, so good night for now, and I'll send out another one tomorrow or Saturday where we will go over this. I've already uploaded this, but I just realized I kind of probably need to add about the equations down here. I forgot about those, so I'm gonna have to upload this again. So right now it's Thursday night at 7:46. If you by 8 o'clock tonight, the new one will be up there. Okay, so let me just make that. So let me go ahead and say good night.